Hello, thanks for clicking. Welcome to another Nargilus 2 production. Today we're going to be learning how to write Taylor polynomial approximations. Okay, this is a three-part series here. Taylor polynomial approximations really are one of the most important things you learn here in the second half of this series chapter. So let's get started and let's see what that's all about. And we'll discover that we actually know a little bit about this already. So here's what I want you to do. I want you to use the tangent line at x equals 0 to approximate the value of f of x equals e to the x at point 2, right? So here's basically what I have. I have a graph. Okay, I have e to the x, 0, 1, and I draw my tangent line here at 0, 1, right? There it is. And here's point 2. And I'm going to use the tangent line to find the value at point 2, and then that's going to approximate the true value of e to the x there, right? So again, we're back in the times where we didn't have calculators. There was no easy way to calculate these things, right? If I were to say to you, what's f of point 2? It's equal to e to the point 2. But without a calculator, it's not easy to calculate. But it's easy to approximate with that tangent line. So let's use that tangent line to approximate that value. Let's go find the tangent line. So to find the tangent line approximation, I need to point on f of x. I'm building my tangent line at 0. I can find the y value by substituting 0 in. E to the 0 is 1. And then I need to find the slope of the tangent line. I can do that with the derivative, but the derivative of e to the x is just e to the x. And then I can evaluate it at 0. E to the 0 is 1. So my tangent line would be y minus 1 equals 1 for the slope, x minus 0. And then now I want to approximate the value at point 2. So I want to take point 2, substitute it in for x, and see what the y value is, because I'm using the line to evaluate at point 2. So y minus 1 equals 1 times 0.2 minus 0. So that's 0.2. Y is equal to 1.2. So f of 0.2 is approximately 1.2. Okay. Now, is that the right answer? Is that the true answer for f of 0.2? No, right? It's an approximate answer. It's close, but it's not the exact answer. So the question is, well, could we find the exact answer? Well, yeah, we'd have to know what e to the 0.2 was to get that. But what we really want to discuss here is how to get a better approximation than the one we already had. Okay, so for example, let's say if I were to ask you to calculate f of 0.2, that's equal to e to the 0.2. E to the 0.2 is equal to 1.2214. So this approximation is actually pretty good, right? But again, the further along the tangent line you go, the further away from 0 I get where I built the tangent line, the worse my approximation is going to be. So the question is, can we find a way to get a better approximation for the whole curve, not just one value of it? All right, so let's talk about what we could do. So can we do better than that? And how would we do better than that? So basically what we did so far is we used the tangent line approximation to approximate the value at point 2, right? This tangent line approximation that you built is actually one example of a Taylor polynomial, okay? It's a Taylor polynomial with degree 1. It's a first degree polynomial, right? Okay, y equals, what was it? Y minus 1 equals 1 times x minus 0. If I put it in slope-intercept form, y would equal x plus 1. Yeah, x plus 1, that's a degree 1 polynomial. So this is a Taylor polynomial with degree 1. So now you might be able to sense what is going to happen here. What happens if we write a Taylor polynomial with a higher degree? What if we wrote degree 2 or wrote something with degree 3 or degree 4. So now we're talking about getting into, well, could we use a parabola as an approximation for the value of 0.2? Could we use a cubic or a quartic or a quintic? And how would we write the equation of those, given that really the only thing we know how to do right now is write the equation of this tangent line, right? So could we write something in the form y equals a0 plus a1 x minus c plus a2 x minus c squared? Okay, well, this would be something that's in quadratic form. This would be degree 2, right? The question is, how would we write something like this? All right. And again, so that we have an idea, and a lot of these definitions are going to be coming up very soon. This C here is called the center. Okay, and by center we mean it's where the line or polynomial is built around. So for example, in my tangent line approximation here, C is equal to 0, right? Because I built my tangent line, I put the point of tangency at 0. Okay, so that's what this C actually represents. So we're going to talk much more about that as we go along. So, but what I'm interested in is building a degree 2 polynomial for this function. How would we go about doing that? All right, so let's write the second degree Taylor polynomial for f of x equals e to the x, centered at x or c equals 0. Okay, all right, so here's what we're going to do. So my second degree polynomial, we'll call it p sub 2 for now, is equal to, well, there's some term a sub 0, then there's some term a sub 1, multiplied by x minus c, and then there's an a sub 2 with an x minus c squared, right? And again, you saw that, or the beginnings of that, when we had our tangent line from a moment ago. Let's put it back up here so that you can kind of see. All right, if I add the 1 on both sides, I would have y equals 1 plus 1x minus 0. Okay, so then here would be your a0, here would be your a1, right? And then this would be linear, okay, or degree 1, because there's really only a first power up there, and that's as high as we go. All right, so how are we going to find these a0, a1, and a2? Well, to find them, you're going to do 3 different things. Okay, so we're centering this thing at x equals 0. So p sub 2 of 0 will have to equal f of 0. All right, so f of 0 is p sub 2 of 0. All right, so let's calculate that first. So f of 0 is 1, right? If I calculate it here, here's f of x. So we'll do it over here. F of 0 is e to the 0. It's 1. So p sub 2 of 0 is equal to 1. So now we're going to have 1 is equal to a sub 0. Oh, hold on. Let's go back here for 1 second. Let's put a step here in the middle here that I think will help people. So p sub 2 of 0 is equal to a0 plus a1. This thing is centered at 0. So that's x minus 0 plus a2 x minus 0 squared. Then p sub 2, let's change this around here. P sub 2 of x, we'll say. Then p sub 2 of 0 would be a0 plus a1, 0 minus 0, plus a2, 0 minus 0 squared. So p sub 2 of 0 is 1. So 1 is equal to a0. So a0 is 1. Plus a1. So to find a1, I need to find the derivative. So p prime of 2 evaluated at 0 is equal to f prime of 0, right? a1 is the slope. Here it is. It's the slope of the tangent line. Okay? So f prime of 0 is equal to, well, f prime of x is e to the 0, or e to the x. F prime of 0 is e to the 0. F prime of 0 is 1. So p2 prime of 0 is equal to 1. Okay? So then, now, if I find p prime 2 of x, I want to find the derivative with respect to x here. So I'm going to derive this with respect to x. The derivative of a0 is a number, so that's 0, plus the derivative of a1 x minus c is going to be a1. The derivative of a2 x minus c squared will be 2a2 x minus 0. And then p sub 2 prime of 0 is equal to 1, which is equal to a1 plus 2a2. X is 0, and that drops out a2. So a1 is also 1. So this is 1x minus 0 plus, okay, now I want to find a sub 2. To find a sub 2, I'm going to match the second derivatives. All right, so let's do that here. I'm going to erase some of this so that we have some room to do it. And then we'll write our final polynomial. Okay. So we're going to match the second derivative. So the second derivative of p, evaluated at 0, will be equal to f double prime of 0. So we know f prime is e to the x. F double prime of x is also e to the x. F double prime of 0 is e to the 0. It's 1 again. And now I need to find f double prime, or p double prime of x. So p double prime of x, derivative a0, 0. Derivative a1, x minus c. Where's that first derivative? Here's the first derivative. So the derivative of a1 is 0. The derivative of 2a2 times x will be 2a2. So p double prime of 2, sub 2 evaluated at 0 is equal to 1. Right? We just calculated that. That's equal to 1 there. And then that's equal to 2 times a sub 2. So a sub 2 is a half. So that's x minus 0. C is 0. Squared. So my second degree Taylor polynomial, p sub 2 of x is equal to 1 plus x plus 1/2 x squared. So this is the derivation of that Taylor polynomial. Okay? All right, so that's our first example. There's 2 more videos to talk about this. There's a lot to talk about here. So stick with it, keep going, and you'll kind of see where this whole thing is headed coming up. As always, thanks for clicking.